Welcome to lecture 16 of EE720. So today we are going to discuss a specific kind of a group, the group Zn star. So just to, as a recap, so what is a group? Group is a set with an operation which satisfies four properties. First is the operation needs to be closed. Second is that there has to exist an identity in the set. Then there has to exist inverses for every element in the set. And finally, we need the binary operation to be associative. So these topics or these properties were defined and discussed in lecture 14. So you can look at the lecture outline for the specifics of these definitions. So let's define this group, define the group Zn star. So we'll define the set and the binary operation and prove that it is in fact a group. So the definition is so you take a integer greater than 1. We define Zn star as follows. It's the set of integers in 1 to n minus 1 such that the GCD of the integer b with n should be 1. So the greatest common divisor with integer b in this range from 1 to n minus 1, and n has to be 1. So this is the set, and to define a group we need to specify the binary operation. So, and the binary operation is going to be multiplication modulo n. Okay, and we're going to verify that these properties, these four properties, let me just show them again. Closure, existence of identity, existence of inverse, and associativity hold for this set here along with this binary operation. So to prove that this is in fact a group, let's check the properties. So closure, if I multiply two integers and I look at the result modulo n, then the the result is going to be an integer from 0 to n minus 1. So that's the, so there is, it's not trivial to check closure here. So for all a, b in Zn star, we need to check that a times b modulo n belongs to 1 to n minus 1. So what we do know is that a times b modulo n belongs to 0 to n minus 1, but we have to ensure that it cannot be 0, because the modulo n operation gives us 0 to n minus 1, but we have to ensure that it is not 0. Then we are sure that or we can hope for closure. The other thing we have to check is that the GCD also, the GCD of, let me just move that a bit. The GCD of A times B and N also needs to be 1. Yeah, because finally we want the binary operation, which is multiplication modulo n. The result of that has to belong to Zn star. So not only should it belong to 1 to n minus 1, but also the GCD of the product. Maybe actually this is not the right, what I should write is AB mod n here. So let me do that here. We need to check that GCD of AB mod n and n is 1. Okay, that's better. Okay. So how are we going to check this? So let's recall a proposition which we covered in lecture 13, which was the first lecture on number theory. So it said that let b and n be integers with n greater than 1 and b positive. Then b is invertible. Modulo n. If and only if the GCD of b and n is 1. And the definition of invertible was that there exists some other integer c such that when you multiply b with c, the result is 1 modulo n. So b is invertible implies there exists an integer c such that b times c equals 1 mod n. And we denote this integer c as b inverse. It's a convenient notation because when you say b inverse, it automatically implies that it is the multiplicative inverse of b modulo n. So how are we going to use this proposition? So notice that let's go back to the definition of Zn star here. So Zn star by definition contains only those integers which have GCD with n of 1. So all the integers in Zn star, all these b's such that the GCD of b and n is 1, all these integers in Zn star, they'll have multiplicative inverses, modulo n. So what do we want to show? We want to show that this AB mod n is never 0. So we'll show that by arguing that if AB mod n was 0, because A and B have multiplicative inverses, I'll just multiply by A inverse and B inverse. On the left hand side, I'll get 1. But 0 times anything is 0 mod n, so I'll get 0 on the other side. So that's a contradiction. So that is how we'll make sure that AB mod n is never 0. And we want to show that the GCD of AB mod n and n is 1, we'll just appeal to this proposition again. Since A inverse B inverse will be a multiplicative inverse of AB mod n, and so the multiplicative inverse of AB mod n exists, so the GCD of AB mod n with n must be 1 because the proposition is an if and only if condition. Okay, so I'll just turn the page and do the mechanics. So we want to show that AB mod n is not 0. So suppose AB mod n was 0 for AB in Zn star. Since AB belongs to Zn star, so the GCD of A with n is 1 and the GCD of B with 1 n is 1. A inverse exists, and similarly B inverse exists. So multiplying on the both sides, so AB mod n is 0 would imply that A inverse B inverse AB mod n is 0 times A inverse B inverse, which is just 0 again. But this is 1 mod n is 0, which is a contradiction if n is greater than 1. Okay, so AB mod n cannot be 0, and since it's a remainder, it has to be from 1 to n minus 1. So hence, since we have what we have shown as so far is AB mod n belongs to 1 to n minus 1. Okay. And so here we already showed that A inverse B inverse is the multiplicative inverse of AB mod n. So since multiplicative inverse exists by the proposition GCD, since the multiplicative inverse of AB mod n exists, so the GCD by the proposition again, so GCD of AB mod n and n is 1. So AB mod n belongs to Zn star for all A and B in Zn star. So we have shown closure. So closure is done. So let's so the remaining properties we have to show are existence of identity. Identity one is the multiplicative identity in this or identity under this multiplication modulo n. Zn star, and it always belongs to Zn star as n is greater than 1. So inverse follows from the proposition again, which says that as long as the GCD of the integer and n is 1, it will have a multiplicative inverse. Well, it almost follows from the proposition. So what follows from the proposition? Let me get this. So it follows from the proposition, the lecture 13 proposition, that there exists some integer, but the inverse property of groups requires that integer to be in Zn star. So we'll just move it into the group, that there exists a C in Z, not Zn star yet, such that GCD of such that B times C equals 1 mod n for any B in Zn star. Yeah, for any B in Zn star. So, but in the group, in the definition of a group, we need the inverse to exist inside the set itself. So we need that C to be in Zn star. Right now, it's only in the larger integers. So we have to bring it to Zn star. So let's consider C prime which is equal to C mod n. Now, so first of all, so the GCD of C prime and n is 1 because B is its multiplicative inverse. Because if BC is 1, if I take mod n on both sides, anyway, this is a mod n, so BC prime will also be 1. All multiples of n will disappear. So B is the multiplicative inverse of C prime. So from the proposition again, this is GCD of C prime and n is 1. So hence, which means that C prime n is greater than 1. So C prime cannot be 0. So C prime belongs to Zn star. So what do we need for something to belong to Zn star? So the GCD of that integer and n should be 1, and it should be in the range 1 to n minus 1. Since it's a modern operation here, so C prime will belong to 0 to n minus 1. We just have to exclude 0. But since C prime has a multiplicative inverse, its GCD with n is 1. So C prime cannot be 0, because if it was 0, then the GCD would be n, which is greater than 1. So C prime is not 0, and so C prime has to be belongs to Zn star and is the inverse of B. So inverses do exist in Zn star. And the last property we needed to check was associativity. So that is just multiplication modulo n. So that is associative in the integers anyway. So we'll not check that. So associativity is we'll just skip that. So this completes the proof that Zn star is in fact a group, and it's going to turn out to be a very useful group for us when we discuss public key crypto systems. So what we have proved so far is that we have defined this set Zn star, and we've shown that it is a group under multiplication modulo n. So let's consider a special case. Suppose n is a prime. Suppose p is a prime. So how does Zp star look like? So what's the definition of Zn star again, or in this case Zp star? If the set of all integers be from 1 to p minus 1 such that the GCD, GCD of B and P is 1. So which integers B will have a GCD of 1 with the prime P? Now all these integers are less than P, and by definition the prime has only two divisors, one in the prime P itself. So all of them will have GCD of 1 with P. So it turns out that Zp star is just all the integers from 1 to p minus 1. Okay. So this fact, along with the fact we've just proven that Zn star, or in this case Zp star, is a group, it allows us to prove Fermat's little theorem using group theory. So what is Fermat's little theorem? It says that if P is a prime, and A is any integer not divisible by P, then a to the p minus 1 is equal to 1 mod p. So if you calculate a to the p minus 1 and you divide by p, the remainder is going to be 1. Okay. So we want to prove this using the fact that ZP star is a group of this form. Let's do that. So the proof is like this. So a is any integer. It need not be in ZP star. So for a in Z, there exists b in ZP star such that a is equal to b mod p. So why can we say that? So ZP star consists of the integers from 1 to p minus 1. If I do modulo p, a mod p is going to be some integer from 0 to p minus 1, 0, 1, 2, 3 up to p minus 1. But the theorem says that the integer a is not divisible by. So the theorem says that a is some integer which is not divisible by p. So a mod p cannot be 0. So there will be some remainder when you do a mod p, which is from non-zero remainders. It has to be from 1 to p minus 1. And that will belong to zp star because we said that zp star and p is the prime. Zp star consists of all the integers 1 through p minus 1. Okay. So then a to the p minus 1 will be equal to b to the p minus 1 modulo p. So all we need to show is that b to the p minus 1 is equal to 1 modulo p. So consider the subgroup angle bracket p, which is consists of the elements b, p square modulo n. So I'm skipping the modulo n here. So the operation implicitly means that we are doing the group operations here. So b square mod n. If I just write b square, it means we're doing the modulo n and b cube and so on. So since ZP star is a finite group, this set is a subgroup of ZP star. And what do we know about subgroups of finite groups? The cardinality of this subgroup will divide the cardinality of ZP star. And the cardinality of ZP star is 1 to p minus 1 because ZP star is precisely these elements 1 to p minus 1. So there are p minus 1 of them. So the cardinality of this subgroup must divide p minus 1 by Lagrange theorem. And what is the cardinality of this angle bracket b? It is the smallest integer k such that b to the k equals 1 mod p. Okay. So this follows from the proof of the theorem where we showed that this angle bracket b, when the group is finite, if you look at take any element in the group, take any element b and look at this angle bracket b set which is defined like this turns out to be a subgroup. In the proof of that, we implicitly showed this statement that what is the cardinality of the subgroup? It is the smallest positive integer such that b to the k equals 1 mod p. And now this k divides p minus 1. So b to the p minus 1 is going to be b to the k times some other integer L, which is equal to b to the k raised to the L, which is 1 raised to L mod p, which is 1. Which is 1 mod. So we have shown the theorem here. So what did we want to show? We wanted to show. So what did we want to show? We wanted to show that uh, for any integer not divisible by p, a to the p minus 1 equals 1 mod p. So we argued that there must be some other element, some other integer b in zp star itself, such that a to the p minus 1 will be equal to b to the p minus 1 mod p. Then we looked at the subgroup generated by that integer b, and by Lagrange's theorem we said that the order of that element or the order of that subgroup has to divide p minus 1, and so b to the p minus 1 is equal to 1 mod p. Since b to the p minus 1 equals a to the p minus 1, we are done. Okay, so let's recall this definition of the Euler phi function, which was discussed in lecture 15, I think. So the definition was as follows. So it's defined for the positive integers. So phi of 1 is 1. For n greater than 1, phi of n is the number of integers in this set 1 to n minus 1 which are relatively prime to n. That is, the integers I in this set 1 to n minus 1 such that the GCD of I and n is 1. Okay. So why are we recalling this definition? So it turns out that by definition, the cardinality of Zn star is going to be phi of n, because it is the number of integers in the set 1 to capital N minus 1 such that the GCD of the integer and capital N is 1. And this gives us Euler's theorem, which is an extension of Fermat's little theorem for the case when the modulus is composite. So for any integer n greater than 1 and a and Zn star, we have a to the phi of n equals 1 mod. So what did Fermat's little theorem say? The difference was that n was a prime and a was any integer not divisible by that prime p. So here we have a is to be in Zn star, and in the Fermat's little theorem we had p minus 1 here, and the remaining part was similar. So if you substitute n equals a prime p, then phi of p will be p minus 1, and any integer in zp star will be an integer which is not divisible by p. But of course, there we said any integer. Here the integer is asked to be in Zn star. We can have a slightly relaxed condition on this, but for us this suffices. By relaxed condition, I meant that you can say that the GCD of a and n is 1, and this theorem would still hold. And the proof will be similar, so we won't do it. Again, what is the proof? So we look at, so A is already in Zn star. So just look at the, okay, maybe I'll just write down a few steps. So consider the subgroup generated by A. So the subgroup will be angle brackets A by A, and its cardinality must divide phi of n, which is the size of the group by Lagrange theorem. And the proof follows in similar manner. Okay. So let's now calculate the value of this Euler phi function for integers of specific forms. Okay. So a lemma here. For an integer e greater than or equal to 1, e stands for exponent here. And prime p, phi of p to the e is going to be p to the e times 1 minus 1 by p. So it's saying that you have a prime p, you raise it to some positive power, and then the answer or the value of the Euler phi function at that prime power is going to be p to the e times 1 minus 1 by p. And why is this interesting? So when n is p to the e, the cardinality of the group Zn star will turn out to be this integer here. So for e equals 1, we already saw that. So if e is 1, p to the e is a prime, and phi of p was just p minus 1. So here p to the 1 will be p into 1 minus 1 by p, so p minus 1. So what is the proof? So what do we need to do? We need to, by definition, check which integers in 1, 2, up to p to the e minus 1 are relatively prime. To p to the e. That is, which integers I in this range have a GCD of 1 with p to the e. So that is the question here. So since we have a prime power here, this is a prime power. So any common divisor of I and p to the e will have to be a prime power. Uh, so I should say that again. So the GCD of I and p to the e is either 1 or some prime power. And the allowed prime powers are p square up to p to the e. Okay, and not p to the e, because we are restricting I to be strictly less than p to the e. So it will be p to the e minus 1, where the e minus 1 is in the exponent. So the easier thing to do, to calculate this number, the easier thing to do is to look at, so when is it not equal to 1? So when is GCD of I and p to the e not equal to 1? So it turns out that any multiple of p, where p is the prime, any multiple of p will have a GCD which is not equal to 1. So we need to find all multiples of p in this range. So what are the multiples of p in this range? So the first multiple is p, second is 2p, 3p, up to. So what is the largest multiple of p in this range? Um, so it will be of the form p to the e minus something, where that whatever we are subtracting here should be as small as possible to make this multiple as large as possible. So it turns out that that um, whatever we can subtract to maintain this, for this to continue to be a multiple, is going to be this p here. So the largest multiple of p in this range 1 to p to the e minus 1 is going to be p to the e minus p. So these are the integers in this range which have a GCD which is not 1, and every other uh, integer will not be divisible by p, and hence it cannot have it'll have a GCD which is equal to 1. So let me just turn the page now. So if I is not divisible by p, then the GCD of I and p to the e, this has to be 1, because if it is not equal to 1, it has to be something which divides p to the e, and the only divisors of p to the e other than 1 are all uh, divisible by p. Okay. So we need to count these, how many of these multiples there are, and remove them from this set. So we need to look at this set here. So 1, 2, up to p to the e minus 1. This is the largest set. From this I want to do a set minus of all multiples of p. P to p up to p to the e minus p. So this number is going to be, so the multiplier here is ranging from 1 to p to the e minus 1 times p, right? So the multiplier, if I take p common here, it will be p to the e minus 1 minus 1. So this is the number of elements which are multiples of p in this set. So we have the cardinality, or the phi of p to the e is going to be p to the e minus 1 minus p to the e minus 1 minus 1, which is p to the e minus p to the e minus 1, which is going to be p to the e times 1 minus 1 by p. Okay. And we are done. Okay. So there's another lemma which is going to be useful in the context of the RSA public key crypto system. It says that for distinct primes, p and q, we have phi of pq is p minus 1 times q minus 1. So you have these distinct primes here, p and q, and it's saying that the number of elements, so the claim is that what we have to show that the number of integers I in this set 1, 2 up to p times q minus 1 with GCD of I time I and pq being 1 is p minus 1 times q minus 1. So we have to show this. So we have to show that the integers in the range 1 to pq minus 1 which satisfy GCD of I and pq is 1 is p minus 1 times q minus 1. So once again, we look at the integers such that this GCD is not equal to 1, and we'll remove it from this range here. So let's consider integers I such that GCD of I and PQ is not equal to 1. So how will they look like? Now, PQ is a product of two distinct primes. So if the GCD is not 1, there's only um, three other possibilities. So GCD of I and PQ can be either 1, P, Q, or P times Q. It's a common divisor, and these are the only possible divisors. We are already saying that it's not 1. So it can only be 1 and PQ. But our I is restricted to 1 to PQ minus 1. So the divisor of I cannot be PQ because I is strictly less than PQ. So then the only uh, uh, non-unit or non-1 GCDs possible are P and Q. So the multiples of P and Q in these P or multiples of Q in this range will have GCD which is not equal to 1. Okay, let's look at those multiples. So consider the set this so multiples of P. So P, 2P. So what is the largest multiple of P which will fit in this range? That is going to be again PQ minus P, and then the largest multiples of or the multiples of Q are going to be Q, 2Q up to PQ minus Q. So I claim that these are all the integers which are either multiples of P or multiples of Q. And I claim that these two sets cannot overlap. So I mean this here and this here. So we claim that these two regions they cannot be any overlap. Because if I times P equals J times Q for some ij such that I is multiples of P are going to be I is going to be from 1 to Q minus 1, and J is multiples of Q, so it's 1 to P minus 1. Then we have a contradiction. Why is that? Oops. So I was not focusing on the screen, so let me do this again. So my claim was that this and this region here, they don't have any intersection, because if I times P is equal to J times Q for some ij such that I is these I ranges from 1 2 up to Q minus 1, and J ranges from so J is multiples of Q, so 1 2 up to P minus 1. If this happens, then we get a contradiction. Why is that? Because by a result we proved in lecture 13, if P is a prime, and P divides a product of two integers A and B, then P divides A or P divides B. So this was a result we proved in lecture 13. And here, if IP is equal to JQ, so by definition, P divides uh, JQ. But P and Q are distinct primes, so P cannot divide Q. So P must divide J. But J was in the range 1 to P minus 1, so that's not possible. So we get a contradiction. So these two sets are disjoint. So this, by sets I mean this multiples of P and the multiples of Q, they don't have any overlap. And these are the only integers in this range. By that I mean in this range here, 1 to PQ minus 1, which have a GCD which is not equal to 1. So how many are there? So there are P minus 1 and Q minus 1. So let's complete it in the next page. So phi of PQ is going to be the cardinality of the set 1, 2 up to PQ minus 1 set minus multiples of P, so P to P up to PQ minus P and Q to Q up to PQ minus Q, this cardinality of this set. So this set has cardinality PQ minus 1, and this is P, or I should say maybe just for clarity. So there are Q minus 1 multiples of P, right? So Q minus 1 minus or plus P minus 1. So this is PQ minus 1, and then there are two minus 1s here, one of them cancels, and you'll get minus Q minus P plus 1, which is going to be P minus 1 times Q minus 1. Okay, so and we have shown that phi of PQ and P and Q are distinct primes is P minus 1 times Q minus 1. Okay, great. So it turns out that for any positive integers, which are relatively prime, so let's consider Mn such that GCD of M and N is 1. We have phi of Mn is phi of M into phi of N. Okay, so this earlier result is a special case of this because we said distinct primes. If M and N were distinct primes, then the GCD of distinct primes is 1, and phi of phi of P would be P minus 1, and phi of Q would be Q minus 1. So this is a generalization of this previous result here, but we will not prove this because this proof will follow from something called the Chinese remainder theorem. So we will not be proving this. So once we have the Chinese remainder theorem, this will follow from as a corollary. Another theorem which we won't be proving is this. So if n is a prime, then Zn star is a cyclic group. So Zn star is a group under multiplication modulo n. So this theorem, which we will not prove, is says that there exists some element such that when you multiply it again and again, it will generate the whole group Zn star. This does not follow from Lagrange's theorem because n is a prime, but Zn star will be n minus 1. The cardinality of Zn star will be n minus 1. So it doesn't follow from Lagrange's theorem. So that ends our discussion of Zn star for now. We will next discuss the Chinese remainder theorem.